In this video, which is the second video about complex numbers, we're going to look at some of the algebra attached to complex numbers. Now, to begin with, we just need to introduce just a little bit of notation. First of all, if we've got z is a complex number, then we use z bar or sometimes z star to denote the complex conjugate of z. So, if z is 3 plus 7i, then the complex conjugate of z is 3 minus 7i. And if w is minus 1 minus 3i, then the complex conjugate of w is minus 1 plus 3i. And in general, if z is p plus iq, then the complex conjugate of z is p minus iq. Now, if z is p plus iq, then we say that the real part of z is p, and the imaginary part of z, or imz, is q. So, if z equals 3 plus 7i, then the real part of z is 3, and the imaginary part of z is 7. And if w is minus 1 minus 3i, then the real part of w is minus 1, and the imaginary part of w is minus 3. Now there's one really important observation. If we know that two complex numbers are equal, then that means that their real parts must be equal, and also their imaginary parts must be equal. In other words, if x plus iy is the same as p plus iq, then x must equal p and y must equal q. So let's now start looking at some algebra related to complex numbers. We've seen how to add, subtract, multiply and divide complex numbers. We haven't yet determined a method of finding the square root of a complex number. So we'll start with doing that. So we're going to try and find the square root of 7 minus 24i. So let's suppose that u plus iv is a square root of 7 minus 24i, where u and v are real numbers. So we're saying that u plus iv is the square root of 7 minus 24i, which is equivalent of saying that u plus iv squared must equal 7 minus 24i. Now, u plus iv squared is the same thing as u plus iv times u plus iv. Multiplying that out, that gives me u squared plus 2uv times I plus v squared times I squared. Remember that I squared is minus 1, so that simplifies to u squared plus 2uvi minus v squared. And we'll just collect together the two real terms, so we've got u squared minus v squared plus 2uv times I. So we can rewrite our equation as u squared minus v squared plus 2uvi equals 7 minus 24i. Now, the left-hand side has got a real part of u squared minus v squared. The right-hand side has got a real part of 7. Similarly, if we look at the imaginary parts, the left-hand side has got an imaginary part of 2uv, and the right-hand side has got an imaginary part of minus 24. Now, since the complex number on the left-hand side is the same as the complex number on the right-hand side, the real part of the left-hand side must be the same as the real part of the right-hand side, and the imaginary part of the left-hand side must be the same as the imaginary part of the right-hand side. So we must have u squared minus v squared equals 7 and 2uv equals minus 24. So we've got a pair of simultaneous equations to solve to find out what u and v are. So looking at the second equation, we can rewrite 2uv equals minus 24 as v equals minus 12 over u. And if we substitute that into the first equation, we're going to get u squared minus 12 over u squared equals 7. In other words, u squared minus 144 over u squared must equal 7. Now, a sensible thing to do with this is to multiply up by u squared to clear the fractions out. And if we multiply up by u squared, we get u to the 4 minus 144 equals 7u squared. And if we get everything on one side now, we've got u to the 4 minus 7u squared minus 144 equals 0. So what we've got here is we've got a quadratic equation in u squared. And we can attempt to solve that either by factorising or by using the formula or obtaining the values of u squared from the quadratic equation solver on our calculators. Factorising then will give me u squared minus 16 times by u squared plus 9 equals 0. So either u squared is 16 or u squared is minus 9. U squared equals 16 gives me u equals 4 or minus 4. U squared equals minus 9 gives me no solutions because we've been quite clear earlier on to state that u and v are both real numbers. So u squared equals minus 9 is impossible for a real number u. So we know that u equals 4 or u equals minus 4. If u equals 4, we've got v equals minus 3. And if u equals minus 4, then v equals 3. So our square roots of 7 minus 24i are 4 minus 3i. If u equals 4, v equals minus 3. And on the other hand, if u equals minus 4, we had v equals 3, so the other square root is minus 4 plus 3i. So we have found two square roots of the complex number 7 minus 24i. Moving on, let's now try and solve a quadratic equation. So we've got the quadratic equation with complex coefficients. So we've got the quadratic equation z squared minus 6i times z plus minus 16 plus 24i must equal 0. So if we would, it's not easy to factorise this as a quadratic equation, but we could use our quadratic equation formula. So if we use the quadratic equation formula, we've got a equals 1, we've got b is minus 6i, and we've got c is minus 16 plus 24i. So z must be minus b plus or minus the square root of b squared minus 4 times a times c, divided by 2a. Now if we work out or simplify this expression, minus 6i just gives me 6i. Minus 6i squared is the same thing as 36i squared, which is minus 36. And then we've got minus 4 times 1 times minus 16 is plus 64. And minus 4 times 1 times 24i is going to be minus 96i. and that's all divided by 2. Now the bit inside the square root simplifies down to 28 minus 96i. And 28 minus 96i has got a common factor of 4 running through it. So if we pull that common factor of 4 out of the square root expression can be simplified to 2 times the square root of 7 minus 24i. So our quadratic equation formula gives us that z is 6i plus or minus 2 times the square root of 7 minus 24i, all divided by 2. If we do the division through by 2, that simplifies down to the fact that z is 3i plus or minus the square root of 7 minus 24i. Now fortunately, we've already worked out the square roots of 7 minus 24i are 4 minus 3i and minus 4 plus 3i. So what we've got now is that z is 3i plus or minus 4 minus 3i, and that gives me that z is either 4 plus 0i, in other words just 4, or minus 4 plus 6i. So we've been able to solve a quadratic equation which has complex number coefficients, and we found that the solution of this equation is just complex numbers. Now in general, if we have any polynomial, not just a quadratic polynomial, but any polynomial at all with complex coefficients, if this polynomial has degree n, then it will have n complex roots. Some of those roots may be repeated, but there will certainly be n complex roots there. And what this is telling us is basically that the whole process of making larger and larger sets of numbers to solve equations has actually finished with the complex numbers. Now at this stage it's worth just pausing for a while and just see whether you can do exercise 1 here, which asks you to find the square roots of 16 plus 30i and minus 5 minus 12i. So pause the video at this point. When you've finished the 2 questions, restart the video to obtain the answers and check your answers. So here are the answers for exercise 1. Now we're going to move on now and have a look at some more ways in which we can work with equations involving complex numbers. So find z if 2 plus I times z plus 3 minus 2i equals 1 plus 2i. Well, this is really just the same structure as the equation 5x plus 13 equals 28, except that the example we've got to consider at the moment is a complex number example. For the equation 5x plus 13 equals 28, we'd subtract 13 from each side to obtain 5x equals 15, and then divide each side by 5. And we're going to do very much the same thing with this equation. So the first thing we're going to do is we'll subtract the 3 minus 2i from each side. That will give me 2 plus I times z equals 1 plus 2i take away 3 minus 2i. In other words, 2 plus I times z equals minus 2 plus 4i. Now I want to find out what z is, so I've got to get rid of the multiplication by 2 plus I, so I'm just going to divide each side by 2 plus I. If I divide each side by 2 plus I, I'm going to get z is minus 2 plus 4i divided by 2 plus I. Now we can either work that out by multiplying top and bottom by the complex conjugate of the bottom, in other words multiply top and bottom by 2 minus I, or if you've got a calculator which will handle complex numbers, we can just use our calculator to do it. Whichever we do, we end up with z equals 2I. Moving on to another example. In this case, we've got 3 plus I times z plus 2I times w must equal 4 plus 10I, together with the equation z plus 1 minus I w equals 3 minus 3I. So we've got a pair of simultaneous equations. The only difference this time is the simultaneous equations involve complex numbers. And we can do exactly the same sort of method as we would have used for normal simultaneous equations back at GCSE level. So, looking at the equations, we can see that if we multiply through the second equation by 3 plus I, then we will have equal coefficients of z in each of the two equations. So, doing precisely that, leaving the top equation alone, multiplying the bottom equation through by 3 plus I. The top equation is unchanged, the bottom equation just becomes 3 plus I times z plus 3 plus I times 1 minus I times w equals 3 plus I times 3 minus 3I. If we tidy up that second equation, we've got 3 plus I times z plus 4 minus 2I times w equals 12 minus 6I. So all we've done at that stage is we've multiplied out the brackets in the line above, where we had 3 plus I times 1 minus I, and we had 3 plus I times 3 minus 3I to work out. Now I can eliminate z from these two equations very easily. So if I do equation 1, take away equation 2, I'm going to be left with 2iw, take away 4 minus 2iw on the left-hand side, equals 4 plus 10I, take away 12 minus 6I. Tidying that up, we've got minus 4 plus 4I times w must equal minus 8 plus 16I. So w must be minus 8 plus 16I divided by minus 4 plus 4I. Now the complex number division there we can do either by multiplying top and bottom by minus 4I, or we can get our calculator to do the work for us. So we end up with w equals 3 minus I, and if we go right back at this stage to the second of the original equations, we'll be able to find the value of z fairly easily. So the second of the original equations tells me that z must be 3 minus 3I, take away 1 minus I times w. So that is 3 minus 3I, take away 1 minus I times 3 minus I. And if we do the complex number arithmetic to simplify z, or again use our calculator to find out what z is, we end up with z equals 1 plus I. So we've solved a pair of simultaneous complex equations. Our next example, we have to find numbers p and q so that p times 2 plus I plus q times 3 minus 2i equals 5 plus 6i. So, if I've got p times 2 plus I plus q times 3 minus 2i equals 5 plus 6i, if I multiply out the brackets, I've got 2p plus 2pi plus 3q minus 2qi must equal 5 plus 6i. Looking at the left-hand side of this equation, and just rearrange it so that the real terms are together and the imaginary terms are together, then we've got 2p plus 3q is the real part of the left-hand side, and p minus 2q is the imaginary part of the left-hand side. So I've got 2p plus 3q plus p minus 2q to lots of I must equal 5 plus 6i. Now, I've got a complex number on the left-hand side equaling a complex number on the right-hand side, so the real part on the left-hand side, 2p plus 3q, must equal the real part on the right-hand side, must equal 5. Similarly, looking at the imaginary parts, on the left-hand side, the imaginary part is p minus 2q, must equal the imaginary part on the right-hand side, which is 6. So I must have p minus 2q equals 6. So I've got a normal pair of simultaneous equations there, which can be solved by any appropriate method to give me p equals 4 and q equals minus 1. In our next example, we're told that 1 plus 3i is a root, or a solution, of the equation z squared minus p plus 2i times z plus q times 1 plus I. And we've got to find the values of p and q. So, if z is 1 plus 3i, then z squared is 1 plus 3i times 1 plus 3i, so that's 1 plus 3i plus 3i plus 9i squared. 9i squared is 9 times minus 1, which is minus 9. So I've got 1 plus 6i plus minus 9, in other words, minus 8 plus 6i. Now again, you can use your calculator for doing that calculation, or you can do the expansion out to obtain the minus 8 plus 6i. We know that if z is 1 plus 3i, then z squared minus p plus 2iz plus q times 1 plus I is equal to 0. So I know that minus 8 plus 6i, take away p plus 2i times 1 plus 3i, plus q times 1 plus I must equal 0. Now I need to multiply some brackets out before I make very much more progress. So I've got minus 8 plus 6i, take away the result of multiplying out p plus 2i by 1 plus 3i. So that's take away p plus 3pi plus 2i plus 6i squared, but 6i squared is the same thing as minus 6. Then add q times 1 plus I, which is the same as q plus qi. So, what we need to do at this stage now is collect together all of the real terms and collect together all of the imaginary terms. The real terms that I've got in the line above is minus 8, take away p, plus 6, add q. And the imaginary terms in the line above are 6, take away 3p, take away 2, plus q. Now we can tidy up that real term and that imaginary term somewhat. So minus 8 minus p plus 6 plus q becomes minus 2 plus 6. Sorry, minus 2 minus p plus q. On the other hand, for the imaginary term, we've got 6 minus 3p minus 2 plus q becomes 4 minus 3p plus q times I. Now that lot has got to equal 0, and to emphasize things, 0 is the same thing as 0 plus 0i. So we must have the real part on the left-hand side equaling the real part on the right-hand side. So we must have minus 2 minus p plus q equals 0. And we must also have 4 minus 3p plus q equals 0. In other words, we've got minus p plus q equals 2, minus 3p plus q equals minus 4. And solving that pair of simultaneous equations in any way that you like gives us p equals 3 and q equals 5. Our final example asks us to find a complex number z that satisfies the equation 3z plus I times the complex conjugate of z equals 7 minus 9i over 2 plus I. Now, the first thing that's probably sensible to do on this question is to work out what 7 minus 9i divided by 2 plus I is. So either by multiplying top and bottom by 2 minus I, or using the calculator, if you've got complex numbers on your calculator, we can do that division and find out that it's 1 minus 5i. So, if z is x plus iy, then we know that the complex conjugate of z is x minus iy, so that the equation can be written as 3 times x plus iy plus I times x minus iy equals 1 minus 5i. Multiply the brackets out, we've got 3x plus 3iy equals ix minus I squared times y, but remember I squared is minus 1, so minus I squared times y is just going to be plus y. And that lot on the left-hand side has still got to equal 1 minus 5i. Collect together the real terms and the imaginary terms on the left-hand side. So the real term on the left-hand side is 3x plus y, and the imaginary terms on the left-hand side are 3y plus x. So we've got 3x plus y plus 3y plus x lots of I must equal 1 minus 5i. So equating the real parts on the left-hand side and the right-hand side gives me 3x plus y must equal 1. Equating the imaginary parts on the left-hand side and the right-hand side gives me 3y plus x equals minus 5. Solve that pair of simultaneous equations gives me x equals 1, y equals minus 2, and this tells us that our complex number is 1 minus 2i. Finally, there's an exercise here of questions involving working with complex numbers to solve equations involving complex numbers. So you might like to pause the video at this stage, have a go at some of these questions, and then restart the video to obtain the answers. So here are the answers. And this concludes the video on using complex numbers algebraically.